לא.
רוצה שאני אעבוד על זה עכשיו כבר נרצה נסיים את זה בעשר דקות.
יאללה,
זה אתם תשתיים. עם יתר.
רגע, ויש תלך. באיזה כיתה היא עושה?
לכל שלב וחצי.
Okay, so today we are starting the second part of the course. After we have studied properties of lattices from the zero temperature lattice, the structure, the forces that exist, there's the different ways it can get organized, how does it respond to temperature, how does it respond to acoustic waves, how does it scatter. We are going to talk in the second half about basically electrical and magnetic properties of solids. And this comes actually from two different sources for two different reasons. First, and that's the reason why I wear this shirt, basically 2/3 of the periodic table are metals. So it's an interesting subgroup of all the elements that exist. Second of all, basically technology, since probably the 3rd or 4th millennia before Christ, is mainly based on metals. Once someone invented bronze and found a better way to hack to pieces his enemies and stones and pieces of wood, you got the Bronze Age. Then someone came up with the idea, well, iron is better. You had the Iron Age. So on and so forth until mid of last century you got the semiconducting age, and whatever your bet is on what's happening in here, will we have something based on carbon, like carbon nanotubes or graphene or things like that, or superconductivity or other things like that. Materials drives a lot of the technology. Okay, so basically we can roughly speak about two groups of materials, metals and insulators. And basically they have a lot of differences. If I'll take this window, you have a representative of both groups in this window. You have here a metal, aluminium, I guess, and you have here glass, which is silicon in some arrangement. And they can't be more different than one another. One is opaque, shiny, but light doesn't go through it. One light goes through it in a very efficient way. That's the reason why we have it in a window. One of them is malleable, meaning I can put a bit of pressure and and change its profile without breaking it. The other thing, try to put pressure on glass and change its shape. Will work only in very high temperatures. At room temperature, you shatter it to pieces. If you measure the conductivity of this thing, so I'm taking an multimeter. I'm sure you've met it in some of your classes here, laboratories, and I'll measure very nice. Let's see. Okay, first of all, if I just shorten it, I get a very small resistance. This should be reasonable metal. Well, let's go to something else. I'm a bit more convinced will. Okay, so probably it has some coatings there, but let's take a piece of metal. Okay, again, a very good conductor. Glass or wood or whatever you want here, terrible conductor. Even your body is quite a bad conductor, a bit better than wood or glass, but still a bad conductor. Okay, so we have metals, we have insulators, and in the middle I'll write semiconductors. Okay, so I've argued that metals are good conductors, insulators are very bad conductors. How good is good and how bad is bad? Well, that's not a very clear criteria. Anyone who has some experience with materials knows that there are metals that are known as bad metals that have really bad conductance. You build, you do power lines out of copper wires for a reason. It's a metal, but you could have iron or whatever as a metal, cheaper, much cheaper also. It's a worse conductor. Copper is the best conductor that is not too expensive. So the criteria of putting some number above it, below it, is not a good criteria. We have to have some better criteria. Okay, first of all, when we are talking about resistance, there are two elements that play in the resistance. Anyone remembers anything out of high school physics? What are the true criteria?
Of electrons on the free layer, maybe?
I don't know. At this point, I don't even know what's an electron. Simpler.
Place on the periodic table.
Simpler. When you did Okay, here we're getting somewhere. There are two components of resistance. One is pure geometry. If I'll take the same material and I'll take a wide conductor or a thin conductor and measure the conductance through it, this will have higher conductance, lower resistance. It's pure geometry. And the second thing is the material from which this conductor is made. So how do we sum up? So we have a heuristic law that you all have learned in high school that says the resistance of such a thing depends on A, the cross section, L, the length, and rho, which is some property of the material. Okay, it becomes larger as the resistance. Oh, you should. A over L. Okay, I wrote it correctly. Resistance becomes larger as the length becomes larger. Smaller as the area becomes smaller. If you want to think about it, it's some generalization of Kirchhoff's and Ohm's law about resistance in parallel and resistance when we are connected in series. In series, in parallel. Simple. And this is a material-dependent constant. We can call it it's basically the resistivity of meter upon meter upon meter cube, if I'm using MKS. And it's material-dependent, but not only material-dependent. What is the most obvious thing that changes even for the same material?
Temperature.
Temperature. And at the moment, we'll look only on this dependence. And actually, this will be our criteria to define what's a metal and what's an insulator. For a metal, rho, when T approaches the absolute zero, in Kelvin units, of course, it goes to some constant. For insulators, goes to infinity. And this is the criteria that as physicists we define what's an insulator and what's a metal. Do we go to a finite value as the density, as the temperature goes to 0, or do we get an infinite contribution to the resistivity, meaning no current goes through at 0 temperature? What about this guy? So these guys behave as insulators under this definition. The current goes to 0, or the resistivity goes to infinity as the temperature goes to 0. Okay, is this all? Well, if we would have been born prior to 1906, yes, there's a very interesting phenomena which is accompanied also with magnetic properties, which is superconductors. But actually much more. What do I mean by much more? If it would have been superconducting only at 0 temperature, it's very hard. Well, it's actually impossible to be exactly at 0 temperature. What's special about superconductors is that this is fulfilled for some temperature which is below a temperature which is known as critical temperature. And since the first discovery of materials that behave in this way, 1906, Kremlin Ons in the Netherlands, there's an ongoing fight to get TC higher and higher. Basically, till the 80s, 1980, the limit was around 30 Kelvin. Okay, it's already usable, but not very usable. Why do I say that? Basically, to go down below the temperature of liquid nitrogen costs a lot of money. On the other hand, for certain applications, you are ready to pay the price. Someone knows here a very famous application?
MRI?
MRI. Why do you need to go to such small resistance there? Because you are trying to create a magnetic field through a coil. And if it would be in room temperature, the heat will just kill it. You won't be able to create a high enough magnetic field. So you need a superconductor. So you pay the price of having a very expensive piece of machinery, which also costs a lot to use. But for that, people are ready to invest money into it. To carry power to your house or to create a levitating train or all such kinds of applications, it's too expensive. In the 80s, they created materials that go above it, but these materials come with another bag of problems. They're not metals, really. They're ceramics. So who cares? Well, even the simplest problem of creating a wire, well, to carry current, you have to have a wire. And metals are wonderful in the meaning that you can play with them, you can pull them, make very nice wires. Look around you, everywhere you have metallic wires. On the other hand, ceramics are brittle, break up, don't bend well. Anyone who has a fiber optics connection at home knows that if you take this connection and accidentally apply too much pressure on it, it breaks up and doesn't work anymore. On the other hand, metal wires, you can bend them, you can do anything with them. So those are materials that exist at higher temperature, not room temperature, much below, usually around 80, 90 Kelvin. But that's if you could have created a good cooling system. It's not too expensive and you can use it. Someone knows what is the current most used application of these materials? Well, it's again magnets. And MRIs that have such magnets are starting to filter into the market. But mainly, nowadays, it's two applications. One is for particle acceleration. Again, something you need very strong magnetic fields to use them. And the second is all this new excitement about fusion. The stellanators, the tokamaks, all these things. It seems to be moving now compared to what it was 20 and 30 years ago, because you can create much stronger magnetic fields at a reasonable price. Okay, so we'll touch upon superconductors in some future date. We have said something about metals. We have said something about insulators. Insulators are also very important. We don't want current to go where we don't want it to go. But a moment ago, or a few minutes ago, I said something about semiconductors. I said that they are insulators. So why do I give it a special name?
The dependence on temperature is much stronger?
Exactly. They depend on physical parameters the resistance is much more sensitive to different external conditions. One of them is temperature, could be light. Anyone who went into a lift and blocked the passage and the door didn't close on him or her, the reason for that was basically you have a light at one side, a detector which is a semiconductor on the other side, and when you block the light no current goes through, so the door doesn't close. And semiconductors, I don't have to tell you, are ubiquitous in all technology that exists, because a rapid change in the resistivity is the basic building block of technology. Why? Because the most important thing about technology is being able to let current go through in one condition and stop it from going through at another condition. And if you have to count on metals, the change in resistance or conductivity is just too slow to be useful to anything. On the other hand, semiconductors are insulators, but the conductance or the resistance change very rapidly with external conditions, and therefore they are very useful in technology from diodes, transistors, and so forth, and we'll talk about it. Okay. So why are we spending half of the course on these materials? That's very nice properties, but what is interesting from the point of view of physics? Okay, so
Hello.
we want to understand why materials are metals, why are they insulators, what's special about semiconductors, what is the physical basis to all these heuristic explanations that I gave. When I say heuristic, I mean basically we described things. At the moment I didn't explain anything. I told you metals behave this way, semiconductors behave in another way. That's not an explanation, that's description. Okay, so our aim is to explain these behaviors. They have also magnetic properties that we will be interested in. You know that iron, for example, could be magnetized. On the other hand, copper or gold or silver, not. Why?
Because it's a ferromagnet.
That's on the same level that here. Of explanation as I'm giving here. It's giving a name to a property. It's more classifications than an explanation. And we'll try to get some deeper insights into these properties. Okay, so we'll go through now a series of theories, more or less in a historical sequence. And why I'm doing that, I'm not starting from better theory that is our current understanding, for two reasons. One of the reasons is the same reason that you start with Newtonian mechanics and don't start with special or general relativity.
Learn to walk before you learn to run.
You learn to walk before you learn to run, and then you could ask me, why don't you start with Ptolemaic mechanics? Because walking here is applicable at least to part of the explanation. At certain conditions, it gives us a good and simple explanation on what's happening. So it's very good to have this mental picture in order to understand, when you are going to more complicated situation, what is the basis. The same thing that Newtonian mechanics can solve you 95% of your problems without going into general relativity or things like that. Second reason is that basically it's interesting to see how we are building a theory for a system that all the time we have things that we don't know about, don't understand, and they are complicated systems. Usually, as a physicist, the course in solid-state physics or condensed matter physics is not a basic course in the meaning that we don't have here new and encompassing theories. We don't learn something like electromagnetism or thermodynamics or mechanics or quantum mechanics. We're describing systems, And the reason that we didn't explain them, part of the systems in the courses that I've mentioned previously, is that they are complex systems, that we need considerations from many different angles of sight in order to understand them. And what most physicists do during the life is not invent a correction to general relativity, but trying to apply the bag of theories they have into to a given system, and to understand what's important and what's not important, and how much of the system you can describe with the theories that you have without to complicate things too much. Okay, so we'll start with trying to understand metals, and we'll go to the year 1907. A guy named Drude that was the first to try to give an explanation on the properties of metals, and we'll see that he, although he thought about it in very general terms, there's nevertheless some grain of truth there, and even something that could be checked experimentally. Okay, so basically I'm now going over chapter 1 in Ashcroft. You may wonder why are we jumping between chapters, because Ashcroft tried to start from the most interesting subject and then move to other things when he needed it, and he created some I would say somewhat chaotic trajectories through the subject. Some people like it. I prefer to handle it in a different way, and that's how we are going here. So that's chapter 1, Ashcroft. And we are looking into so remember, it's about 1907. People, the term electron was introduced just 10 years previous to that time. So it's a very new concept. Second, lattices. First X-ray diffraction experiments were around 1904, 1905. Again, very new. Even the concept of atom wasn't yet well established. Bohr's model of an atom, 1913. Understanding that you have even a nucleus and electrons around it, around that time. So he's playing here, trying to explain a system where he's missing a lot of the ingredients, or totally missing, or it's very new concepts that are not yet well understood. So it's amazing how good this very simple theory works. So, what was Drude's concept? Well, we have a metal. And we have their atoms. And these atoms have electrons. And Drude, without having a good reason for it, remember Bohr was just 5 years in the future, decided that some of the electrons are very strongly bound to these atoms, meaning they are out of the game. And these are core electrons. And some number of electrons, usually assumed to be of order 1, when I say order 1, it could be 2, 3 pair atoms, are free electrons living everywhere in this matter. Okay. How do we treat these free electrons? He assumed that we treat them in the simplest way we can think about. And the simplest way we can think about is actually, if you think about it deeply, it's deeply flawed. What do I mean? He thought about the free electrons as a gas. Of electrons that can have collisions with the atoms, and that's all. They have no interactions between themselves. Now, if you'll think about it a bit, when you have studied the theory of gases in thermodynamics, ideal gas, it made sense in the meaning that atoms or molecules are neutral objects, that we can imagine that they don't feel any influence of any other atom unless they collide, getting a very short distance between them. Electrons are entities with charge. Charge is long range. Coulomb interaction is long range. So, why does he assume that electrons don't know about each other? That would be the first thing we would come and say. Sorry, electrons should know about each other.
Maybe symmetry makes it all cancel out.
They repel each other.
Occam's razor. First try, and if it doesn't work, try something more complicated.
That's the crux of the issue. Indeed. Before you go into a more complicated theory, assume something very simple. If it fails, add layers of complexity. But at first stage, look what happens in the simplest case, and then move on. We'll see. It's not completely crazy, because if we look on the average, we have here a sea of electrons, but we have also positive charges. We know that the metal in general is neutral. So you could wave your hands and claim, look, the effect of all the electrons plus the effect of all the positive ions somehow will cancel out. Let's forget about it.
Well, why should the electrons collide in the first place? They repel each other. They should collide only with the protons.
Well, to repel is to collide. Right? Go, the experiment that proved that you have a nucleus in an atom, Rutherford experiment. What did he do there?
Gold sheets.
It took a very heavy atom, or relatively heavy atom, gold, and what did he shoot at it? No. Alpha particles, or helium atoms where the two electrons were stripped off. That's an alpha particle. What's special about an alpha particle?
Low penetration.
You can make it easily with the radioactive decay.
All of this is true, but not relevant to what I'm trying to explain. It's positive. It has 2 protons. The nucleus is positive. So they repel each other. Nevertheless, he did an experiment of scattering. Can scatter the only thing about it is that you have to give it enough kinetic energy to get close. But there's no reason that you can't scatter charges off each other. Okay, so that's his model. Let's see what it gives you. And here we'll throw in elements of the theory of gas and other things that you know from thermodynamics, like average velocity in a gas and so on and so forth. So let's do it step by step. Okay, first question is what is the density of these free electrons? Or to be more exact, what is the charge density of the free electrons? Okay. Let's assume that we have n atoms. Okay, let's start with our definition of the charge, just the density of the free electrons. N atoms Z free electrons per atom. At that time he had no idea what is this number Z, how is it connected to a specific atom, and so on. Just plugs in a parameter. Number. Divided by the volume. Okay. Nothing too exciting about it. What else would it be?
Volume of who? Who's the volume?
The metal.
Of the whole metal?
Yeah, I have n atoms in this piece of metal. Each one of them contributes Z electrons. And the density is divided by the volume.
Do you raise the charge density there? The charge?
I erase the charge. If you want to, if you want to do the charge, just multiply it by E, the charge of an electron.
Of course.
Something that, again, they knew, but it was very new. Millikan and the oil drop experiment. I want to define another quantity. Which is Rs, which is the distance between electrons.
Between electrons, the electrons are just everywhere.
It's a typical distance between electrons. Taking the volume, dividing it by the number of electrons.
4/3 pi rs cubed, that's just like the typical volume then.
Right.
Where there's one electron.
Right. And
But the,
I divide the volume by the number of electrons times Z. That's the total number of electrons there, right?
We don't need to take into account the volume of the other particles in the metal?
Quick and dirty. First of all, as you know, where can I be quite sure that I don't have electrons there? Today's knowledge.
The nucleus.
In the nucleus. What is the volume of a typical nucleus compared to
To the whole cloud of
Nothing.
electrons is
Angst-
nothing.
nothing?
Okay.
So I don't have to worry about it. Why Drude didn't worry about it?
didn't know.
Malcolm's razor.
He also didn't know.
He didn't know anything. He assumed you have here some structure, don't care about it. The electrons fills the whole metal, and I'm only interested in the volume of this metal. That's all. So this is 1 over NE. And if you want to pull out RS, something that Drude didn't know, but nowadays we know. What would be the typical length scale that we should compare the distance between the three? Or radius. So, at some point we'll ask ourselves the question, what is the ratio between the Bohr radius between the distance between the electrons and the Bohr radius? Okay, very nice, very good, but how do you measure this thing?
Charge?
No, it's neutral.
Entropy stable?
Remember, a piece of metal is neutral. Free and for each positive charge you have in the nucleus, you have a negative electron somewhere. What do I measure here? Free electrons. But how do I separate the charge that comes from free electrons to charge that comes from
With an electric field.
Exactly. I have to do an experiment where I put an electric field and see what flows and what doesn't flow. Because unless I have an electric field, there's no way I can separate between free and bounded electrons or core electrons. So this is not a nice definition, but at the moment I have no way to probe it. Okay, when we're speaking about a gas, what is a fundamental concept about this gas?
Pressure? Volume?
Ideal for gas?
Hmm?
No, never mind.
What separates a gas from a single particle living?
Interaction.
Larger number of particles?
Yes and yes, but let's refine this definition. You have other particles and therefore you have collisions. That is something that doesn't exist when you have only one particle. You don't call one particle in a box a gas. You call 10 to the 23 particles a gas. And since in an ideal gas we assume that there's no long-range forces, nothing beyond scattering, so it's the collisions of the electrons with other particles. In this case, Drude didn't care if the collision is with other electrons or with other particles or with the ions or with anything else. Doesn't matter for it. What does matter is what happens between collisions and what happens in collision. Okay, so assumptions. Okay? Well, so that's an ideal gas assumption. what's a collision? Suddenly you have a different momentum. Could someone check the spelling of collisions? I have.
It's another L.
Two L's.
Without one of them.
I have. I had the feeling that it can't be right. Okay. So we have to give a time scale for the collisions. Collision happen every some seconds. Okay, so if instead of time I can look on rate, which is one of the times, the number of times I have collisions per a second or per an hour, per whatever. So tau minus 1 over tau, is the rate of collisions, therefore tau is the time between collisions.
Isn't that an average time or something like that?
Of course, we're doing here thermodynamics, everything is average. There's no way that we will try to describe each electron, its path and the number of collisions and whatever.
You also can't.
You
An electron doesn't, you can't label an electron anyway.
But let's say we're dealing here with a classical theory, remember 1907. Even if you could label it, there's no way, and even if you had a way, you wouldn't want to follow the same logic that stands behind the kinetic theory of gases. No one wants to follow 10 to the 23 atoms in a gas. No one wants to follow order of 10 to the 23 electrons in a piece of metal. What does that mean? Well, first of all, practical. If I have resistance, put a finger on it, it feels that the resistor becomes hot, meaning that not all the energy is conserved in the electrons. It's dissipated as heat into the environment. And basically it tells you that could I ask, we didn't have the problem till now, but please mute your phones. Okay, so these are the four assumptions. Let's take these assumptions and try to understand what they tell us about the electron. Okay, so first step, we'll go back to high school and remind ourselves, what does Ohm's law tell us? this is not the volume. Okay, we define the resistance. What is I? I can write it down. Instead of the total current, I can write it down as a current density. Because I'm throwing in a lot of concepts that all of them you know, but they're coming from different areas of physics, so I'm trying here to remind you what is each quantity, so that's the current density. What's nice about it? Instead of current using this, we eliminate the area of the conductor out of the gate. Okay. Now, instead of looking on what is the voltage that we are applying on the system, let's ask what is the electric field. Again, high school physics. And the nice thing about that is we have thrown out all of the geometry out of the game. And again, you could tell me we have known it from electromagnetism. Can't get any response. Read your responses. Yes or no? Does it ring a bell? And just to remind ourselves, these are vector properties. Okay. All this is electromagnetism. Now we can look on it from the point of view of electrons that are carrying the current in this game. What is the density of the current? Well, number of electrons times the charge times the average velocity. So I'm sorry that everything here is V, volume, voltage, and velocity, but I'm trying to give it, here I gave the volume with bars over the V. Here it's just V, and here I'm giving a curl on this. So this is the velocity, average velocity.
Why is the minus there?
Don't remember
Charge.
who's the guy that insisted on defining the charge of an electron as negative, but
Franklin?
we're carrying it since then.
I think it's Franklin.
Who?
Benjamin Franklin.
Not sure. Could be, but really can't recall at this moment. So anyway, whoever decided on that did a great disservice to physics. We have to all the time remember to put in the minus.
So E is just defined as positive.
E is defined as positive. If you remember, current is also defined as a motion of positive charge probably for the same reasons. Doesn't really matter. I could have put here QE and then I didn't need this might. Okay, so now let's go back to Sir Isaac Newton, and if I have a field and I have a free electron, free particle, what is the velocity?
What's the right?
I hope I don't have to explain this. But, and here I'll do something that you can't do. I'm not interested in the velocity of a specific electron at a specific time. I'm interested in the average of these velocities. See, here I'm interested in the average. Okay? So I'll average. The average of V0.
The constant. The average is itself.
It's 0. Because after each collision it comes out at some direction. The simplest assumption. It has no preferential exit direction after the collision, meaning that if I average over V vector, it's 0.
Oh.
The charge is not an averageable quantity. E is constant, M doesn't change. What is the average T? The average time before it gets itself smacked in another collision and loses all velocity, right? So it's tau.
Unit 1 over tau.
No, I defined the rate as 1 over tau. So tau is
Okay, so okay.
Okay. So I can go back to here. And if I look at what's written here, where sigma is conductivity. Is this generally true? The answer is no.
It's only in linear materials, right?
Right, but for the moment, let's just assume that the conductivity is 1 over the resistivity. Okay, so what is my conclusion? I had here two minuses, so I should have a minus from here and a minus from here. Let me write it down in a clearer fashion. So measuring the resistance or the conductivity in Rude's theory depends on the number of electrons, the charge of the electron, times between collisions, and the mass of the electron.
How are you supposed to measure the time between collisions?
Okay, now let me rephrase your question. E, I know. Millikan went and measured it. M, I know. Someone remembers?
9 times 10 to the minus.
Not a number. How do I know it? Or how, in principle, I could have known it. Modern physics, all those experiments in a vacuum tube that you send a particle, if you know the charge, you can balance electric and magnetic forces, and from that you can pull out the mass of the particle. So I know the electric charge, I know the mass. If I knew one of these two things, I could have pulled out the second one. How do I know one of these two things? Well, I measure the conductivity and I have two parameters that it depends on. So if I had some theory that forces me to say that you have 1, 2, 3 electrons per atom, perhaps you could pull out this number. It doesn't work. this number is not an integer number, which is a problem actually for Drude, but we'll touch it in a moment. Can I independently measure one of these two quantities? And the amazing thing is, yes. Perhaps not so amazing. We just have to remember what I described to you a couple of minutes ago. How did I measure the mass of an electron in a vacuum tube? I applied
An electric field.
and a magnetic field on this metal. Let's do the same here, which is known as Hall conductivity or Hall resistivity, after the physicists first thought on doing this experiment. Okay, so what is So in general, what is the Hall effect? I take a conducting bar, I apply electric field in this direction, I apply a magnetic field perpendicular out or into the plane. I take a voltmeter, and I measure some voltage, which is known as the Hall voltage on the system. In a moment we'll understand why. But that's a Hall effect. Okay, let me just write down the forces that are applied here on an electron in general, so we would be able to take into account the forces applied by the magnetic and electric field on an electron that exists here. Okay. It's rewritten, what's written here? V is P over N. Again, most of this lecture we are doing high school physics, nothing beyond it. Here we are doing a step that wouldn't have gone down too well in the typical high school, just because we are using a bit of differential language. Okay, what is P at the moment t plus dt? Okay, two things are playing with this electron? One of the things,
The electric field.
the electric field, but let's, electric field, magnetic field, forces. Let's be more general. Okay, because we have two things in the game, we don't want yet to specify what it is. And the second thing that occurs?
Collisions?
Collisions. Okay, so if there were no collisions, the change in the momentum is the original momentum plus the change in momentum that occurs due to the application of force. Impetus, if you hark back to the beginning of mechanics. F times dt is the change in the momentum. What is new here? That we added something that doesn't exist in Newtonian mechanics, which is these collisions that transfer energy out of the system. And what does it mean? That with a certain probability, everything goes to zero. The momentum goes to zero because I had a collision in this period of time dt. And what is the probability? Depending on tau. So I combined my Newtonian mechanics with that come into here, and the fact that I have collisions. Yes, that's something that, to the best of my knowledge, no one speaks about in high school. Okay, but that's an assumption of thermodynamics. Energy is thrown out for a certain reason. Okay. What did I do here? Rearranged a bit the quantities appearing in the equation and
First order approximation.
first order approximation. I threw out dt squared. Nothing that you didn't see many times previously. So this screams of a differential equation. So now I have a differential equation that describes the motion of the electron within the system, and I have the regular Newtonian contribution and Drude's contribution. That's the additional terms that I have because of the fact that the electrons go through collisions here. Okay, what should I add into my mix? I have to write down now the F in an explicit form corresponding to the experimental conditions and try to solve this equation. Lawrence. Is this all?
No, there is also an electric force here.
Right.
Collision.
No, collisions are handled here. If the other term is Lorentz, and this is
Coulomb.
Coulomb. Let's call it. Okay, these are the two ingredients that we have in the game. And just let's stop a minute and see, actually, is this all that happens here? No, we have to be a bit more careful. Okay, this is the magnetic field. This is electric fields that we apply in order to create current. We have an additional electric field. Why is that?
Maxwell's
Electromagnetic.
equations.
Excuse me?
Maxwell's equations.
Electromagnetic, because the electric field generates magnetic one and the other.
No, we're not doing electromagnetic. What does the electric field do here? Excuse me, the magnetic field. We have a velocity in this direction.
Makes him move around.
Moves the particles.
Affects
I
them.
never remember the direction. Is it up or down here? Creates here an excess of charge, just because it always pushes these electrons in the same direction, up or down, either if it's inside or outside. Play with your right hand and remember the directions. And when does it stop?
When there are no more free electrons.
No,
There are
much
enough-
earlier.
When there are enough
When the
electrons,
surface is full of charges.
When
they create
this part
Cancels out the force.
cancels out the force, the Lorentz force. So I don't have only Ex, I have also Ey. That's the reason why I measure voltage here. Because if I have an electric field over a distance, that gives me a voltage. So it gets to a steady state once the condition is that EY is equal to what I get from the Lorentz force. Okay, let's get everything here together. Basically, what am I doing here? I'm connecting this piece of metal to a battery, starting to run the experiment. It gets to a steady state, right? What happens in a steady state?
No current.
No currents in any directions, or this is equal 0, right? In a steady state. So I'm writing down the equations that I start with. Which is this part and the forces. And let me separate it to the x direction and the y direction. I have here two directions.
Don't we need to add the force EY?
I wrote E that
Oh.
includes both. If there wasn't such a field, I would have here only EX. So in the x direction, because Py cross Hz gives you something in the x direction.
Why? No, never mind about it.
Just because this is in the x
Yeah, I know
direction.
cross product or something else.
Okay? So, here I know everything. Omega C is something that I know. Should go through these equations and see what I'm getting out of it. And we'll do that in the next lecture.
מחשב, זה לא מחשב הזה.
לא שמתי לב. אנחנו יכולים להניח שהאלקטרונים הם חלקים שמתנגד חיים שמתנגד לקריאה ביניהם.
גם חלקיקים שדוחים מתנגשים. זה למה הבאתי את הדוגמה של מסודר. זה שלח את החלקיק א' שהוא חיובי, שהתנגש עם הגרעין שהוא חיובי, נגיש, למרות שיש לו.
אתם מסוגלים כבר כאילו כולם מסתכלים לראות את המספוקח. כן. אולי קטן שאני לא זוכר. מאיפה ה-C הזה מגיע בפלורנס שלי? כאילו Q. זה נורא
זה נובע מה-H.
אתה מנרמל את
אתה מכיר אותו B קרוס B.
נכון.
בגלל שאני מתעסק פה בחומר ואני לא רוצה להכניס גם מקדמי מוביליות.
אתה יודע?
אמרנו שיש בעצם שאחת מהם קשורה לכך שאנחנו רוצים כל הזמן לראות איך בונים מערכת כשכל הזמן מדברים על דברים שלא יודעים עליהם ושהם מפרדים אז מה הייתה הסיבה הראשונה?
למה אנחנו עושים את זה היסטורית? אחד, כי זה נותן לך נקודת, בדיוק כמו בחוקי ניוטון, שאתה יכול להגיד למה להתחיל ללמוד חוקי ניוטון, תתחיל בג'נרל רלטיביטי, אבל זה הרבה יותר מסובך, והמון דברים אתה לא צריך את זה, זה נותן לך את ההתנהגות הנכונה גם בלי להיכנס.
זאת אומרת, מה שאתה בעצם אומר זה שהסיבה הראשונה זה שזה נותן לי נקודה להתחיל ממנה שהיא לא מורכבת מדי, ואתה אומר שהדבר השני זה שככה אנחנו רוצים להבין יותר דברים על המורכבות יותר אחר כך. ואז אמרנו שזה בעצם שתי סיבות למה אנחנו משתמשים במודל, נכון?
לא, מתחילים מהמודל הפשוט, למה אני לא מתחיל בתורה הקוונטית המלאה של מוליכות חשמלית.
אוקיי, סבבה. פה, איך הגענו לדבר הזה שכאן?
עכשיו נעבור הביתה.
פשוט משווה נפחים.
זה נפח, אז זה נפח הזה? הנפח הזה כאן זה פי, כן, מספר, פה ראשון מספר אטומי, הוא נצטרך שזה המספר הזה שכאן.
אז זה הווליום פר אלקטרון, וזה גם הווליום פר אלקטרון.
אוקיי, הווליום פר אלקטרון מול הווליום פר אלקטרון פה. ואז אנחנו יודעים שזה גם שווה אחד לשני, ואז בידלנו. עכשיו, אמרנו, אנחנו צריכים פה בעצם שדה מגנטי להפריד אותם קשור לחופשי. פעם בבקשה להסביר למה אני אוכל את זה?
לא, פה אני עוד לא יודע כלום, פה אתה, איך אני מודד את הרס, אין לי דרך למדוד את זה.
כל השאלות של המבחן יהיו משאלות שהוא מעלה כל שבוע.
בצורה בלתי תלויה, צריך איכשהו, וזו המטרה של כל השיעור הזה, להגיע לאיזה משהו שייתן לי מדידה ישירה.
זאת אומרת, אתה אומר שבעצם צריך את השדה המגנטי כדי לבצע את ההפרדה, כדי לקבל איזשהו נתון מסוים. על הרדיוס אתה רוצה לקבל?
אני רוצה, כמו שאמרתי פה, ברגע שאני יודע את NE, אני יודע את הרדיוס. אבל NE, אם אני אמדוד רק זרם, NE יהיה לי מעובב בטאו, איך אני מפריד אותם, איך אני יודע מי שייך למי.
רגע, אבל למה לא נגיד השתמשנו בשדה חשמלי כדי להפריד, למה דווקא שדה מגנטי?
כי שדה חשמלי נותן לך את סיגמה, זה בדיוק הקשר הזה.
אוקיי, כאילו נותן לי פרמטר אחד ולא נותן לי עוד פרמטרים.
נכון, אז אתה יודע את המכפלה של שתי פרמטרים, אתה לא יודע את מה שייך למה.
והשדה המגנטי לאחר מכן נועד כדי לתת יותר אינפורמציה על...
תראה שהוא ייתן על אחד מהם ולא על השני, אז אתה יכול...
כן, טאו לא על NE או על NE ולא על טאו, כי השדה המגנטי בעצם נועד להפריד לי בין המטען הקשור למטען הלא קשור, וברגע שהוא מפריד ביניהם אז אני יכול לדעת משהו נוסף על המטען. כאילו על המטענים החופשיים אתה מתכוון. שזה מה שאנחנו רוצים. אוקיי, סבבה, זה הבנתי. רגע, פה אנחנו יודעים לסבור רדיוס בשלב הזה, נכון?
דרודל לא ידע אותו, אנחנו ידענו.
אנחנו יודעים, אז במרכז בגלל זה אנחנו נגיע לפה. וזה פה הגענו בקיצור עם בידוד כאן. אוקיי, כאן, כשאמרנו שזה שווה סיגמה E. סיגמה יכול להכניס את זה בחומר ליניארי, או שזה יכול לכל חומר?
בכל חומר סיגמה יכול להיות טנזורי. אז אני יכול לקבל זרם בכיוון אחד מהפעלת שדה בכיוון אחר. כרגע פשוט הנחתי שזה לינארי.
זאת אומרת שזה קבוע על כל החומר שלי, לצורך העניין.
לא קבוע, גם לא תלוי בכיוון.
שהוא קבוע ולא תלוי בכיוון? כן, אבל אם הוא קבוע, ברור שהוא לא תלוי בכיוון.
לא.
קבוע זה כאילו קבוע על כל המרחב, אני מתכוון.
לא, הוא יכול להיות אותו דבר בכל המרחב, שבכל נקודה במרחב תפעיל שדה בכיוון X ויהיה לך זרם בכיוון Y.
זאת אומרת, אתה מניח פה בעצם, אוקיי, חומר ליניארי לא קשור לזה עם סיגמה קבוע או לא קבוע, זה פשוט...
זה פשוט קשר, האם זה סקלר או טנזור?
כן, אבל אנחנו אומרים שהוא קבוע פשוט, לצורך העניין.
וסקלר.
קבוע וסקלר, מצד שכאן. אוקיי, סבבה, מסכן. אוקיי, אז אמרנו פה שאנחנו נגיע לזה באמצעות השדה החשמלי, ואז אנחנו רוצים למצוא את הקשר בין השניים האלו שלנו. שזה מה שרוצים לעשות, והשדה החשמלי אנחנו נגיע לו מכאן. אוקיי, סבבה. עכשיו, כאן, כל אפקט, מה זה אומר? מה זה התופעה הזאת בדיוק?
שאני מפעיל שדה חשמלי בכיוון הזה ושדה למעלה ואני מקבל פה מתח.
אני מקבל פה מתח שאותו אתה מודד כאן. אוקיי, ופה זה ה-NE. זה כדי להיות פה. NE. וזה ה-P של חלקיק אחד. J כאילו P שתנה, של זה אחד, ואז עשינו פה את הדבר הזה. ואז אמרת שיש שם אחד נפרד לכל אחד מהשני.
לא, אמרת שיש שני תרומות. יש לך את התרומה מהכוחות, השינוי בטנאלטי בכוח, והשינוי בטנאלטי בהתנגשות, שזה הדבר שמתחיל.
ושתי המשוואות האלה לא אותנו שם, פיתוח מכאן.
תהרוג אותה. רגע, מה יש פה עכשיו? מדע.
ואת זה לא רצינו להכפיל בתוך זה.
זה אנחנו נכנסים.
וואי,
אני פשוט היה פה כוח, התחלנו לזה הכוח מגנטי.
לא, זה הכוח הכלום.
ואז פה היה בעצם את הפייסקל, אבל...
זה פשוט משהו.
היה אומר לא הקשבתי בכלל.
אז יש לנו משמעות של זה הגברה.
אמרתי, לא הולך עליהם. אמרתי, לא נגיד במתמטיקה, לא עושים? יש לה יותר מזמן.
יש את ארז.
יש את ארז, גם מה שמה? זו שהייתה לנו בהכנה.
כן, שרים.
היא לא הייתה עם כזה טובה, אבל היא הייתה עם טרית. הייתי מסוגלת להקשיב לה.
עמוס חייתי כרגע. עמוס היה טוב. אני אהבתי את
זה יכול להיות מרצה טוב, אבל השאלה כמה כאילו יש לי מוטיבציה להקשיב לו, אוקיי?
כן.
מרצה כריזמטי, אני רוצה להקשיב לו.
בשיעור האחרון.
אמרו לי, אתה רוצה לקרוא? לא רציתי להקשיב.
הוא היה בטירוף, אבל הוא לא היה...
הוא לא היה נורא, אבל נגיד,
הוא לא היה ערך.
כשאתה עכשיו הקמנתי, עם כל הכבוד, אני לא רוצה להקשיב. אני לא מעניינים אותי.
תלוי בחומר. מה שלמה מתמטיקאים? איפה כל החיים?
הם לא היו גם במתמטיקה.
לא מגיעים היום?
בואו נעשה קולוסאור, בואו נעשה קולוסאור. קולוסאור. מה זה שציירתי קולוסאור בחדר שלי ככה?
אנחנו מסיימים עוד קולוסאור.
מה
עשית הפוסטר?
לא, ציירתי אחי. זה קולוסאור, זה לייטקום.
די, מי אמר? אני ארוג את מי שאמר. אני ארוג את מי זה היה דוד
זה לא מחיק, רגע, שיט. לא משנה. בסדר, הכל טוב. אבל זה לא מחיק ממחק, זה מחיק...
מה העניין?
אוקיי. אתה רואה, זה לא מחיק טוב ממחק. זה הניתוח בכלל. הכל טוב.
אמרה גם אותה, אבל די.
נראה לי אני אלך.
אני למעלה, מקסימום תירדם, אחי. עכשיו למעלה.
לפחות יש מישהו יותר קרוב.
אתה לא גר פה גם. אתה לא גר בארץ.
לא, אני לא אלך הביתה.
הביתה אני הולכים ברגעים אותן כאילו...
מבטיחות שלא.
אני ביחד רק... די כבר! מה זה? זה מהרצאה שלנו בחשמל, לא?
וואי, נראה לי אתה עייף רצח, אחי, אתה לא, אתה לא שולט מאוד.
אני תמיד צוחק.
הוא היה נותן לי 0, הוא לא אפילו היה בודק במבחן, אפילו שיש לו 100, עניתי לו כל מחר. הוא פשוט היה בא לו לא לבדוק במבחן.
מה זה?
הרסתי את כל איך אתה גם?
תחזור הביתה. אוי.
אני לא קיבלתי פטור בשיעורי מתמטיקה. לא, אני לא סובלת אותה.
כן, כן.
יש הרבה מהם גם פה, נכון? גונן תכמן הכל, גם פה.
גונן סופר, כן,
אני אכפת ממנה.
ממש פה, ביציאה.
ביציאה השנייה.
ביציאה לכיוון...
כן.
כן. תפסיק.
היא מתה עליי.
אחי, עזוב אותי, תן לי לצייר את כל
ביי
הסרט.
מליסוול.
היא יושבת כנראה.
מה
נגיד
התחלת
פעם אחת
להגיד?
הגעתי ביום שני.
מה התחלת להגיד? יש הרבה מודיעין, גם האיים מודיעין, לא? סיוון.
מה זה סיוון?
לא רואה אותו.
הקוקו הזה.
אני לא רואה שאתם קוקו.
זה הקשה, זה הדדי.
אני לא רואה אותו.
איפה הם? גם אתה לא נגיד, חברה שלה.
למה אין לה?
לא מגלה.
היא לא נותנת לי.
איזה קורס
אמרה לי,
גם אצל עמוס.
אני קיבלתי ציון
כן, זה ראיתי.
אמרה לי, תקבלי שנה הבאה. אני מהמרת שאני
רואה
לא
אותו.
אקבל שנה הבאה.
יהיה
מתמטיקה.
אשור אותה לדעתה בעינקים, לא פה.
נראה לך שזה מעניין את הספר?
לא, לא הבנתי, אמרתי אולי הם
מה
עזבו.
זה? מנסה להבין, מה זה?
דיפי לדיפי.
לורנץ, אחי.
לורנץ, אחי.
למה הוא בכל מקום הבן אדם הזה, אחי?
אחי, כי לורנץ פסיכי.
לא, והיה מישהו שקראו לו לורנץ. משהו שם משפחה לורנץ.
לורנץ, נכון.
לורנץ, אחי.
אתה רוצה לומר את לורנץ?
לא, לא הוא, היום. אני פגשתי היום אתמול מישהו.
אז אולי זה נכד שלו.
לא, איזה שם.
אולי זה נכד שלו.
רבי, אהבתי את השאלה האחרונה
אתה
במודרנית.
מנסה איתו שם.
השאלה שצריך להשתמש במטריצה?
שמע, חשמל משהו.
וואלה, שאלה טובה.
שמע, אבל אני אוהב אותם.
הסברתי אותה לאיזה מישהו
לא מבין, אתה מבין?
פיזיקה.
תשאל אותו, תעצבן אותו.
שיעורי בית?
לא, שיעורי בית לא עשיתי, האלה למחר.
אבל זה בחירה שלך.
כללי, אתה מבין את השיעורי בית?
תגידו, יש למישהו את ה...
לא, זה אחד של נשים.
אתה לא יכול כימיה?
עכשיו,
מה?
משחית,
אני לא יודע מה
הם בקבלים.
של מיכאל?
של יונתן.
הם לומדים קבלים, השאלה אם באמת יהיה לנו...
הלכתי למיכאל הודעה.
הם לומדים קבלים, אנחנו לומדים כבר...
בביולוגיה.
למה, סיימנו את כל הקבלים, סיימנו מעגלי זרם, סיימנו מגנטוסטטיקה, עכשיו אנחנו באלקטרומגנטיקה. אנחנו איזה 5 נושאים לפניהם. השאלה אם זה טוב או לא.
זה לא טוב. הוא יגיע ליחסות. לא, באמת
לא, באמת, לא מצחוק. זה מה שרועי אמר. שהספק להגיע.
יש לי 40, מה 35?
אז 15 כולל פיזיקה.
מה הסוג של סיימת?
לא, יש לי 20 כולל פיזיקה.
רגע, כמה...
אשכרה.
יש לי טייפסיות, אני מחשב.
ביולוגיה זה עוד 5.
וזה ממש הכל בסדר.
מה לא נחשב? אני כבר לא יכולים לנוע מהדיון. לא, אין דבר שאני... לא, תשמע, יש דברים שיותר ודברים שפחות.
זה מעניין, זה מזמן, נותנים על מחלות, נותנים
לא נותנים אותה, או שאתה לא אומר.
חשבתי על דברים
כן, אני גם אמרתי.
אתה ממש אלקטרון, גם גל וגם חלקיק, והוא נמצא בסופר פוזיציה.
וואו!
למדת ממריו, אה?
למדתי עשה איזה דוקטורט,
מגדל את הבסים.
מגדל את הבסים?
אתה צריך מחלה.
הוא עשית בכל דבר.
אחי, לא מתאמן.
נכון.